In this video, we want to investigate integrals involving the exponential function e to the x. And the first thing we're going to look at is we're going to remind ourselves of what the indefinite integral of e to the x is. So just as a quick reminder, the indefinite integral, that means antiderivative. Okay. So when we write the antiderivative, we will put a little elongated s. You're going to have a e to the x, that's the integrand, and then we put a dx, and the dx tells us that the variable of integration is going to be the variable x. And as we had learned earlier, um, since e to the x is its own derivative, that means e to the x is its own antiderivative. Now, when you find an antiderivative of a function, you really have a family of functions that comes out. So we always have to put a little plus c because, um, adding any constant isn't going to affect the derivative of e to the x. So let me put a box around this. And then let's shade that box in just, so it gets the importance that it deserves. This is a very famous, very important antiderivative for us. We'll use it a lot in this class. And let's take a look at an example. So let's take a look at an example 6. So one of the things that I like to do is I like to convert my integrals from radical form into exponential form. So I'm going to write this as e to the x to the 1/2 power divided by x to the 1/2 power, like this. And then our variable of integration still stays as dx. Now, when I look at the integrand, I see we have e to something that's not just x. This is e to the x to the 1/2 power. So this x to the 1/2 is a little bit troublesome. So what I'm going to do is I'm going to let u be equal to that x to the 1/2 power. And, at this point, we only know two types of integration techniques. One is change the way it looks, and the other one is u substitution. So I'm going to use u substitution in this case, and I'm going to let u be equal to this x to the 1/2 power. So what I want to do next is I want to differentiate this. So I write du dx, and that's going to be the derivative left-hand side. I'm going to differentiate the right-hand side. So I'm going to get 1/2 x to the negative 1/2 power. And what I want to do next is I'm going to treat this derivative du dx as a quotient of differentials. So I'm going to treat each of these guys as their own little piece there. And what this allows me to do is this allows me to solve for dx. So when I solve for dx, I'm going to get du is equal to 1 over 2 x to the 1/2 dx, like this. And what I'm going to do now is I'm going to solve for dx. So I'm going to isolate the dx, so that this tells me that my dx is going to be equal to 2 times x to the 1/2 power du. Okay. Now when I go back to my original question, I am going to make some substitutions. I'm going to have the integral. I'm going to have e to the u, because that's what my u was. My u was x to the 1/2. I'm going to temporarily leave this x to the 1/2 in the denominator and pray that it cancels out. And then I'm going to replace the dx with the expression I just solved for dx. So this is going to be 2 times x to the 1/2 du, like this. And now I see something great has happened. The x to the 1/2 on the bottom cancels with the x to the 1/2 on the right there. So my integrand simplifies to the integral of 2 e to the u du. Now, we see that we have our integrand is just multiplied by this constant 2. So I can always factor a constant out of the integral. So this is the same thing as 2 times the integral of e to the u du. And this is a simple antiderivative for me to evaluate. I know that the antiderivative of e to the u is just e to the u. So this is going to give me 2 e to the u plus c. I can't leave my answer just in terms of u because my original question involved dx, not du. So what I'm going to do last is just substitute back. So I get 2 e to the x to the 1/2 plus c. And that's going to be my final answer. I'll highlight that like this. Let's look at an example of a definite integral next. So if you look at an example 7 is a definite integral. Definite integrals have these limits of integration over here. So let me just make a little comment here. This is a definite integral. So when I calculate definite integrals, my final answer will actually be a number because definite integrals are really areas under curves. So when I look at this integral over here, and I look at the integrand, I see I have e to some complicated power. So just like before, we can only integrate e to the x or e to the u. We can't integrate e to anything complicated yet. So what I'm going to do is I'm going to make a substitution. I let u be equal to negative 2x, and I want to do the same thing I did before, so I'm going to have du dx. In other words, I differentiate the left-hand side with respect to x. And when I take the derivative of the right-hand side with respect to x, I just get a negative 2. And I'm going to solve for dx again. So I get du is equal to negative 2 dx, which tells me that dx is equal to negative 1/2 du. Next, what I want to do is I want to change the limits of integration. So let's do that. So originally in the problem, I have x is equal to 1, and I want to see when x is equal to 1, what does u become? And all I need to do is take this x value of 1 and substitute 1 into x for the u equal to negative 2x. So this is going to be negative 2 times 1, which is equal to negative 2. Okay, I'm going to now change the lower limit of integration. So the original lower limit of integration was u equal to 0. And same thing, right? I'm going to take 0, I'm going to plug 0 in for x right here, and then that will give me my new u. That will give me my new limit of integration. So I'm going to have u is equal to negative 2 times 0, and that's just going to give me 0. So let's put this all together and repackage it into our definite integral. My original question was the integral from 0 to 1 e to the negative 2x dx. And what I'm doing is I'm changing the integration variable to u. So I'm still going to have that integral sign, but instead of the lower and upper limits being 0 and 1, which are x values, they're going to be 0 and negative 2, which are u values. My e part stays the same, but the exponent will now be u, because that was my substitution. And I want to replace the dx with the negative 1/2 du, like that. Okay. So there's a few things I can do at this stage. I have a constant in times my entire integrand. I can move that constant outside of the integrand. So I'm going to put a negative 1/2 integral from 0 to negative 2 e to the u du, like this. And some of you might look at this integrand and you might be bothered because you have a 0 is actually larger than negative 2. So what we can do is we can interchange these limits of integration. When we interchange those limits of integration, in other words, if I put an integral from negative 2 to 0, e to the u du, you're going to pick up a negative sign anytime you interchange the limits of integration. So this would be a 1/2. There was already a negative there, and now there's like another negative. So I only write that in so you know what just happened there. And as we all know, a negative times a negative gives you a positive. So we just make that a plus. Okay. Finally, I need to find the antiderivative. So the 1/2 stays there. The antiderivative of e to the u is just e to the u. And this time we are going to put a little vertical bar here. We're going to put the lower limit of negative 2 and the upper limit of 0. And I want to make a comment. My comment is, since we changed everything to u, we don't need to change back to x. Okay, changing the limits means you don't have to change back. So we could finish this off by evaluating our integrand at the 2 points there. So we're going to get a 1/2. I'm going to put parentheses here. We're going to substitute in the upper limit of integration, which is 0. And we're going to subtract what we get when we substitute in the lower limit of integration, which is negative 2. So just to finish this off, we're going to have 1/2. E to the 0 is just 1 minus 1 over e squared. Simplifying, we get 1/2 minus 1 over 2e squared. And that it will be our final answer. All right, everybody, this concludes our examples of integrals involving e to the x. Take care, everyone.